right, welcome everyone. So today, after lecture, just a reminder, the exams will be, graded exams will be posted on Gradescope, so you can go through and look at the score you received. And if you have questions, I'd like you to go to recitation this week to see if you got something wrong, to really understand what you got wrong. And so for the next exam, you'll be able to try that question again. Well, something similar. It'll be testing the same learning outcome. So you'll be able to try it again essentially next week for full credit. All right, so keep a lookout for that after lecture today. You'll be able to see your graded exam on Gradescope. For today, we're going to be looking at learning outcome DC3 and learning outcome DC4. So for this one, we're going to just be investigating a little bit more about what derivatives actually are, so what they're measuring. So in this learning outcome, we're going to be able to determine where a function is differentiable given either the graph of the function or just a formula, and be able to explain why. So let's just first recall the definition of, essentially what it means for a function to be differentiable. So we say a function f is differentiable at x, provided our usual limit exists. So the limit of f of x plus h minus f of x all over h, it's the limit as h goes to 0. And that's what it means for a function to be differentiable. That limit exists. So we say that f is non-differentiable at x. So we're defining what it means to be non-differentiable if this limit does not exist. So if the limit exists, our function's differentiable at x. If it doesn't exist, then it's non-differentiable at x. And so just a reminder, this is the formula for f prime of x, our derivative. And so when we do this difference quotient that we're calculating, this f of x plus h minus f of x all over h, when we look at it, it should involve both x and h terms. But when we actually calculate the limit as h goes to 0, that limit kind of gets rid of all of the h's that we see, and we're only left with x's. So we calculate the difference quotient. It involves both x's and h's, but then when we actually go through and finish doing the limit as h goes to 0, that process should get rid of all the h's. And so in the end, if our function f has x as a variable, then the new function f prime also has x as a variable. So f prime should not depend on h in any way. There should only be x's. And so if f is a function, when we do this process of differentiation, we get a brand new function that we call f prime. So it's helpful to think of f and f prime as just two separate functions. And so we could think about the domain of f prime. What is the domain of this brand new function? Well, it's just all x values where this limit exists. So we go through this process of calculating a limit, and for every x value where that limit exists, that x value is in the domain of this new function f prime. And something just to keep in mind is that this may be smaller than the domain of the original function f. As we're going to see, there might be x values in our function where our function is non-differentiable. So the limit does not exist. And we're going to see that in our first example. So we're going to look at the square root of x. And we calculated this derivative before. So we saw that the derivative of square root x was 1 over 2 times square root x. And the domain of the square root function, this is one we've talked about. The domain of that is the closed interval from 0 to infinity. So we can plug 0 into the square root function, that's fine. We can plug positive numbers in, but we can't plug negative numbers in. Now when we look at this new function f prime, we see that it still has a square root, so we can't plug negatives in, but now we also have a fraction. So we have to be careful where if we have division by 0, and we do have division by 0 at x equals 0. So we have to throw x equals 0 out of the domain of this new function. So let's look more specifically at what's happening. Why are we throwing x equals 0 out? Well, one reason is because we're looking at this function, and this function is just undefined at x equals 0. Because it's giving us division. But more specifically, what's happening is that if we were to calculate the limit, we would see that the limit, the definition of derivative, that limit definition of derivative, that limit does not exist. And so more specifically, at x equals 0, we would see that the limit of f prime of x, as x gets closer to 0 from the right, would be equal to positive infinity. And actually, we have the graph here, so we can actually see that. We can see that right in our graph. So if we look, we have our regular square root function graphed, and then we also have f prime graphed, the derivative. And what we see is if we look close to x equals 0, f prime has a vertical asymptote at x equals 0. So as x gets closer and closer to 0, what's happening to our derivative? Well, the derivative is going up and up and up. It has a vertical asymptote at x equals 0, and we can see that also with our limit going to positive infinity. Now, what's happening in our original function is that directly at x equals 0, so if we look at our square root function, what's happening there? Well, we have what's called a vertical tangent. So our original function f has a vertical tangent at x equals 0. So if we were to, if we were looking directly at x equals 0 and trying to sketch what the tangent line would look like, the tangent line to the curve would be straight up and down. It'd be a vertical line directly at x equals 0. And so because our function f has a vertical tangent there, its derivative, f prime, has a vertical asymptote. And more specifically, f prime does not exist at x equals 0. So this is going to be something we're going to see more in just a few minutes. When our function has a vertical tangent line, its derivative does not exist there. All right, so that's what we're going to lead up to here with differentiability, is we want to be able to think of differentiability in terms of graphs. And so we've seen this idea before where the slope of a curve at point P is defined to be the slope of the tangent line to that curve at point P. And so we have our, in this little diagram here, in this little example, we have our curve. And then we have our point P, and we've drawn in what our tangent line is. And to really think about what it means to be differentiable at a point on our curve is if we were to zoom in, kind of zoom in on that point. We would get a graph that looks like this. And what we see is that it's very difficult to tell the difference between where the curve is and where the tangent line is. Specifically, right around that point, it's very difficult to say, okay, here's my curve, here's my tangent line. It's very difficult to tell the two apart. And so what the tangent line does is it gives us a really good approximation of what the curve is behaving like directly at that point. So it's the straight line that gives the best approximation of our curve. So you can see that by just looking at this, directly at that point P, it's the curve and the tangent line look very similar. They overlap. So another way to think of this is that our curve looks like a line near point P. And so really that's the idea of what a differentiable function means, is that if you were to zoom in on each point, zoom in really close to each point, the curve is actually just going to look like a straight line. And so kind of the graphical interpretation of that is that a function is differentiable provided its graph does not have any abrupt changes or vertical tangents. So when we think of abrupt changes, what we mean here is that there's two things to consider. Any jumps or breaks in the graph, or just sudden changes in the slope of the graph. And that's what we're looking for. So abrupt changes, we can think of them very abrupt as just a sudden jump or a break in the graph, or maybe something a little more subtle where our slope just had a abrupt change. And graphically, there's just a few types here to consider. And so we're given 5 graphs here, and all of these are non-differentiable at x equals 2. And in the first graph, the very first one here, this is where we're seeing kind of a sudden change in our slope. So if we look at this curve, we're seeing a sudden change in the slope of our curve directly at x equals 2. And why is it sudden? Well, on the left side here, we have positive slope. Our curve is going up. On the right side, we have negative slope. Our curve is going down. And directly at that point, at x equals 2, it's not a smooth transition. It's a very sudden kind of sharp change from a positive slope to a negative slope. And that sharp, abrupt change, we kind of give that a special name. We normally call that a cusp or a corner. And so differentiability the idea of being differentiable has a connotation of our curve being smooth. So no kind of jagged edges like that, no abrupt changes. In the second graph there, we've seen one like this before. This one is where we have a vertical tangent line at x equals 2. So if I were to plot my point there and draw in the tangent line, it would be straight up and down. So that's another case where that process of doing the limit of our f of x plus h minus f of x all over h, doing that limit, we would get that it doesn't exist. So it's non-differentiable there. And for a vertical tangent, what would happen is that we would actually be getting a infinite limit, just like we saw with that square root function. All right, so those are two examples. Now we might even have more drastic examples. So if we go to the second row, in the second row there's just a clear break in our graph. So there's a jump at x equals 2. So there's no nice way to define the tangent line at x equals 2 for that. Same thing in the second graph here. Here we have an infinite jump. So again, there's no nice way to define a tangent line where there's an infinite jump in your graph. Or even if there's, as in the third one, a hole in the graph. And so we've seen all of these graphs before when we talked about discontinuous functions. So let me get rid of that. So these three graphs are discontinuous at x equals 2. So they're not continuous at x equals 2. And these three graphs are also non-differentiable at x equals 2. So there's no derivative at x equals 2, and there's just a break or a jump in the graph at x equals 2, meaning they're discontinuous. Now the two up here, though, these are a little bit nicer. So both of these are non-differentiable. So the first one has a corner or a cusp. So there's just a sharp change in the slope. Or in the second one, it was a vertical tangent line. So they're both non-differentiable, but we could draw those graphs in one continuous movement without taking our pen off the page. So these are continuous. So we could draw those graphs without ever taking our pen off the page. So we've seen some graphs here that are non-differentiable but continuous, and we've seen some graphs that are non-differentiable and discontinuous. And we're going to come back to that idea. There is a relationship between discontinuities and non-differentiable points, and we'll see that in just a few minutes. But let's look at an example. Let's do a little bit of calculations. So in this example, we're going to determine whether the following function, piecewise function, is differentiable at x equals 20. So the function is c of x, and it's equal to 100 plus 12x when x is between 0 and 20. And then it's equal to 180 plus 8x when x is greater than 20. And we see kind of the graph here. And if we look at that point, might be a little subtle, but you might see a corner at x equals 20. So there's it's a little slighter than what we saw in the previous example, but there's this bend, there's a sharp corner there. And so what we're going to see is that this is non-differentiable. It's going to be non-differentiable at x equals 20. Right now we're just kind of doing a visual inspection of the graph. Just a little bit more kind of reasoning. If we look at the first piece of our function, 100 plus 12x, that's just a line, and the slope of that line is 12. So this left piece over here from 0 to 20, the slope of that is 12. And then if we look at the right piece, the right piece is defined as 180 plus 8x, also just a line, and the slope of that line is 8. So the slope of the right piece here of our function is 8. And so we see this sudden change going from one side to the other side at x equals 20, where we go from having a slope of 12, all of a sudden we have a slope of 8. So there's this sudden change in the slope at x equals 20. And so just more reasoning for why this is non-differentiable there. But let's actually calculate the limit. So what we want to calculate is the derivative here. See if we can calculate c prime of 20. So we want to do the derivative, which is the limit as h goes to 0 of c of 20 plus h minus c of 20 all over h. And let's see what happens when we calculate this limit. So we've already kind of built it up that there's sort of a right piece of our function and a left piece of our function at around x equals 20. So that means to do this limit, we're going to have to consider both the left and the right limits. So let's start with the limit as h goes to 0 from the right. So this is where h is just a little bit bigger than 0. And let's fill in what that, fill in the rest of our limit here. It's c of 20 plus h minus c of 20 all over h. And we want to see what happens when we plug in 20 plus h and 20 into our function. So let's start with that 20. So when we plug in 20, we go up to the piece of our function that's defined at x equals 20. And we see that right here. This is telling us x is what happens when x is equal to 20. And we're using this piece of our function, 100 plus 12x. So let's plug 20 into that. All right, so what about the 20 plus h? What do we do with that? Well, 20 plus h, if h is positive, 20 plus h is going to be bigger than 20. So we go up to our piecewise function, and we see that what happens when x is bigger, or our variable that we're plugging in is bigger than 20, we're right here in this case. And so when we plug 20 plus h in, we're actually going to be plugging it into this piece of our function, the 180 plus 8x. And then we subtract. So if we evaluate all of this, let's see what we get. We're doing the limit as h goes to 0 from the right. And then we just do as much arithmetic as needed. So we get 180 plus 160 plus 8h minus 100 minus 240 all over h. And cleaning up, all those numbers add up to 0. So 180 plus 160 minus 100 minus 240, all of those just add up to 0. So we're left with the limit as h goes to 0 from the right of 8h over h. The h's cancel, so we're left with just an 8. And the limit of 8 is 8. So this is sort of our right side derivative. And that confirms what we kind of did just with graphical inspection. We saw that the slope was just 8 on the right. Now let's try to see what happens if we do the limit coming from the left side. So we're going to do the limit as h approaches 0 from the left. And for that side, h is now going to be negative. And we know it's important, so 20 plus h, if h is negative, this is going to be less than 20. So we fill in, we have just our regular derivative expression there. Now, 20 plus h we said was less than 20. And so we go back up to our piecewise function, and we want to see which piece of our function are we going to plug that into. Well, when x is less than 20, we're in this first piece here. So we're going to be plugging into that. And I forgot, just noticing here, that limit was h going to 0 from the right. Here we're going to 0 from the left. I'm going to plug 20 plus h now into that first piece, so I get 100 plus 12 times 20 plus h. And then I plug 20 into my function c, and we did that one before. We got 100 plus 12 times 20 all over h. And then let's just multiply things out. So we get 100 plus 240 plus 12h minus 100 minus 240 all over h. And then do all the arithmetic, and the 100 and the negative 100 cancel, 240 and minus 240 cancel. So we're left with just the limit as h approaches 0 from the left of 12h over h. And then again, the h's cancel, and we're left with just the limit of 12, and the limit of 12 is just 12. So what we're seeing here is that the left-hand limit and the right-hand limit are not the same. And that's why we're getting this non-differentiability at x equals 20, is because since the left-hand limit and the right-hand limit are not the same, the overall limit, which is how we've defined the derivative at 20, that overall limit does not exist. So this confirms our original claim just from inspecting the graph, that this function is non-differentiable at x equals 20. So this is the sort of procedure you would go through if you were trying to determine if a piecewise function was differentiable at a point. Kind of have to consider the left and the right side limits separately and see if they match up. All right. So this example, let's just keep looking at this graph for just a second. This example, the function is continuous. So if we were to trace over this graph, we could trace over it without ever taking our pen off the page. So it is continuous, and particularly it's continuous at x equals 20, but we just showed that it's non-differentiable there. So like we kind of mentioned earlier, there is a relationship between differentiability and continuity. And so there's this result that says if your function f is differentiable at x equals a, then the function f is automatically continuous at x equals a as well. So this tells us actually a few things. First thing, every differentiable function is continuous. So that's a nice result. If we can do the derivative, then we know that there's no jumps or breaks in the graph of our function. So that's just a nice result. As we're going to see, derivatives, we're going to have some rules that allow us to quickly calculate derivatives without having to go back to limits every single time. So if we can actually do the derivative, well then that actually tells us that there's no jumps or breaks in the graph where our derivative is defined. As that last example shows, though, not every continuous function is differentiable, though. So it doesn't go in the other direction. So if you know your function's continuous, it doesn't tell you anything about differentiability. It might be differentiable, it might not be. So not every continuous function is differentiable. And that's what the last example showed. That function was continuous, but when we actually went to look at the derivative at x equals 20, the derivative didn't exist. So not every continuous function is differentiable. All right, so if we do have a differentiable function, then we automatically know it's continuous. But if we know f is discontinuous, so if we know if we know that our function is not continuous at x equals a, well then we can automatically conclude then that it's non-differentiable there as well. So this theorem really tells us two things. It tells us that if our function is differentiable, then it's continuous. But if our function is discontinuous, then it's non-differentiable at that a value. All right, so let's see this in action. Let's look at an example, another piecewise function. And we're going to determine whether this piecewise function is continuous and differentiable at x equals 15. So this piecewise function is defined as the first piece is 200 plus 2x when x is between 0 and 15. The second piece is 400 plus 2x when x is between 15 and 30. And then the third piece is 600 plus 2x when x is between 30 and 45. And just to kind of help us picture what's going on, we have the graph there to the right. And if we look at x equals 15, what can we kind of say? Well, it's discontinuous there, and it's non-differentiable there. It's going to be non-differentiable there as well. So let's just review, though, how to actually show a piecewise function is not continuous or is discontinuous. And that's what we're going to consider first. So let's say we didn't have our graph. We just had this function. What would we do? Well, we would calculate the right-hand limit of our function. So we're interested in x equals 15. So let's see what happens to our function as we approach 15 from the right. So this means x is slightly bigger than 15, which, if we look it up in the definition of our function, means we're in that second piece. So we would use this as our function. So this would be the limit of 400 plus 2x as x approaches 15 from the right. Now 400 plus 2x is just a polynomial, so to evaluate this limit we can just plug in. So we get 400 plus 2 times 15, and that is 430. So these are just the beginning steps for what we would do if we were trying to show that a piecewise function is continuous. We'd also need to check the left-hand limit. So we're going to approach 15 now from the left, and that's where x is going to be less than 15. So we need to see which piece of our function we're going to use. So we go up to our graph, or we go up to the definition of our function, and we look for what happens when x is less than 15. And we're in our first piece. So we're going to use this piece of our function. So we'll do the limit of 200 plus 2x as x approaches 15 from the left. Now that is a polynomial, so we can just plug in to evaluate. So we get 200 plus 2 times 15, which is 230. And so putting those two together, what we see is because they're different, the limit of cx as x approaches 15 in general does not exist. So the reason the left-hand limit does not equal the right-hand limit. So because that overall limit does not exist, the left-hand and the right-hand pieces are different, what we can say is that this function is discontinuous at x equals 15. And then without even going to check the differentiable limit, we can automatically conclude then that this function is also non-differentiable there as well. So because it's discontinuous at x equals 15, automatically there's nothing left to check. It means it's non-differentiable there as well. All right, so that'll do it for this first learning outcome that we're going to look at today. So really being able to investigate where a function is non-differentiable graphically, but then also be able to kind of look at the formula of the derivative and determine if, from the formula, if it's differentiable or not as well. So that's what we've seen in this learning outcome. For the next one, we're going to kind of look at some applications, look at some more applications of where derivatives are used, or where they might show up. And so for this learning outcome, we're going to see a lot of times in applications, we're sort of missing information about our function. And so there's going to be a need to be able to estimate the value of our derivative graphically or numerically using difference quotients. And then because we're talking about applications of derivatives, we'll want to be able to interpret, well, what does that actually mean in some sort of context? And if there's units involved, we want to be able to state the units as well. All right, so let's first look at some general definitions of gadgets that we've already seen before. So last week we looked at two problems. We looked at our tangent line problem, and then we also looked at our velocity problem. So how do we calculate the instantaneous velocity for an object moving in a straight line, or how do we calculate the slope of the tangent line? And so for our tangent line problem, we were generally considering a function f of x, where this was giving us like the height. And then for our velocity problem, we were considering a function like s of t, and this is really giving us the position of our object that's moving around. And how we kind of got to the slope of the tangent line, or got to the instantaneous velocity, the first thing we did is we calculated, in the case of the tangent line problem, we would do the slope of the secant line. And for our velocity problem, we calculated the average velocity. And that's what we're seeing with this first gadget here that we're defining. Is in general, when we're just talking about just some arbitrary function f, the average rate of change of f of x over the interval from a to b is that gadget we looked at before, f of b minus f of a over b minus a. And in the context of the tangent line problem, that was just the slope of the secant line. And in the context of velocity, that's the average velocity over a time interval. Now, to actually get the slope of the tangent line, what did we do? Well, we did the limit as that second point moved closer and closer to our point P. Or for instantaneous velocity, we did the limit of our average velocity over shorter and shorter time intervals. And that's what we're showing here for just some arbitrary function f. So if we do the limit as b approaches a of f of b minus f of a over b minus a, the way to interpret that for just some arbitrary function f is that represents the instantaneous rate of change of our function directly at x equals b. So we have the average rate of change, and then we have the instantaneous rate of change. And then we also saw before another way to define these is another is just to convert it into f of a plus h minus f of a all over h. And so the instantaneous rate of change would be the limit of that as h goes to 0. So that's just an alternative way of calculating this instantaneous and average rate of change with that slightly alternative version. So either way is okay. We tend to use these versions a little bit more, but either one's okay. All right, so let's see how to estimate the derivative graphically. So in this graph here, we have the graph of just the function x squared. So here's our function x squared. And we want to use that to estimate the derivative at x equals 1. All right. So we're interested in what happens directly at x equals 1 here. So let's plot the corresponding point on our graph. So normally we call that point P. And so f prime of 1, the derivative of this function at x equals 1, we could interpret that as just the slope of our tangent line at that point P. So how do we estimate the derivative? Well, we're going to draw in the tangent line, and then we'll estimate the slope of the line that we drew. So hopefully we get a good sketch here. So we want a tangent line that looks like, when we draw it in, we want it to look like it's just touching the curve. So maybe something like that. So that looks pretty good. We have our curve, and then we're drawing in what we think is the tangent line. And so what we're going to do is we're going to estimate the slope of that line that we just drew. So how do we do that? Well, we already have one point on the line, point P, and what we can do is we can just pick a second point. And when you do that, you just try to keep it easy. So you look for where the line might intersect a grid line or something like that. So you want to keep it easy, if possible. Not always possible, but look for where it crosses a grid line. And the slope is then just the change in y over change in x when you're going from one point to the other. So if we look at to go from point P to that second point that we drew, we would go to the right 1 unit, and then we would go up 2 units. So right plus 1 unit, and then we're going up plus 2 units. And so that's our change in y. And this is our change in x. And so when we do the slope, it's change in y over change in x. And so because our change in y was going up, we went up 2 units, it would be plus 2. And because our change in x was to the right 1 unit, it would be plus 1. And so we see that f prime, or we see the slope of our tangent line here, is equal to 2. Now this is just an approximation because we just kind of sketched in what we thought the tangent line was. So this is really just an estimate. And the reason is because, well, we just sketched the tangent line. So we sketched in what we thought the tangent line would look like, and then estimated the slope of that line. So we might have been off in our sketch, but that's okay. This is just how we would estimate the slope of our tangent line graphically. So to give it a little bit more context, what we're doing with derivatives, we can think of the derivative as just a slope formula for our curve. So, it would be nice if there was a formula that just told us exactly what is the slope at this point on our graph. And there actually is. So this is, again, our curve y equals x squared. And we've done it before where we've actually looked at the derivative of that function. And we've seen that the derivative is 2x. And what the derivative function does is it tells us the slope of the curve, or our tangent line, at any x value. So, we looked at x equals 1. We kind of estimated it before, but at that point 1, 1, the slope of our curve is how we would calculate it exactly if we knew what our derivative was. So assuming here we've gone through the derivative calculation and saw that the derivative y prime is equal to 2x, we can just find the slope then at that point by just plugging in the x value. So it would be 2 times 1, which is just 2. And that confirms what we kind of estimated before by just sketching in the tangent line. Now there's functions where we might not be able to actually calculate the derivative and get a nice formula. So the best we can do possibly is just a graphical estimate. And we'll see that in just a few minutes. But let's just see what happens if we wanted to calculate the slope of our graph at x equals -1. So x equals -1 means we're at this point over here. So -1, 1. And we would just plug in x equals -1 into our derivative, and that would tell us what the slope of our curve is at that point. So it would be 2 times -1, which is equal to -2. And let's just confirm that for ourselves. So let's sketch in what we think the tangent line might look like. That's no good. This is going to be tricky. No, not too bad. All right, so there's kind of an idea of what our tangent line might look like at that point at x equals -1. And just to confirm that it does have a slope of -2, let's pick a second point on that line, so maybe like right here. And what we're seeing is that we go down 2 units and then to the right 1 unit. So we're going down 2 units, and then we're going to the right 1 unit. And so the slope is change in y over change in x, but change in y here is going to be negative because we're moving down. So it'd be -2, and then change in x, we're still moving to the right, so that's still positive. So it'd be +1, so our slope here would be -2. And so we can kind of see here, when our tangent line is pointed down, our slope is negative, and when our tangent line is pointing up, our slope is positive. All right, so let's try an example where we have a function and we're going to have to, the best we can do is just estimate the slope of the tangent line. All right, so here we have a function f of t, and all we know about this function is the information given in the graph. And this function describes the population of the US 10 years after the beginning of 1800. So we're going to be talking about this. There's a few parts to this example here. So let's just really see what this function means. So the graph here, the units on the vertical axis are going to be millions of people. And the units along the horizontal axis, this is given in years after 1800. So for example, let's just see what this function's doing when we say f of 10. What does that actually mean? Well, this is going to be the population of the US in the year 1810. So 10 years after the year 1800. So that's what this function represents. So in the first part of this example, we're going to find the average rate of growth of the US population from 1840 to 1870. And for the purposes of our graph, 1840 means t equals 40, and 1870 means t equals 70. And so the average rate of growth or another way to think of that, the average rate of change, is that formula we saw at the beginning. It's going to be f of 70 minus f of 40 all over 70 minus 40. So we need a way to be able to kind of figure out what these function values are. What is f of 70 and what is f of 40? We're going to get that information from our graph. So we go to t equals 40 on our graph and we look at the point on our curve. And what we do is we just have to estimate, well, what is the y value or what is the vertical value of that point? So t is 40. And if I was reading this, that point is somewhere between 10 and 20. Looks a little closer to 20, so I might say something like 17. Then same thing at t equals 70, find the point on the graph. And this one actually doesn't look too bad. I might say that happens at 40. So that point would be 70, 40. And so what these y values represent what that 17 represents, say, that's our function value evaluated at 40. That's how we read a graph. The y-coordinate is the function value evaluated at the x-coordinate. And so this one would be f of 70. So we're just looking at the y-coordinates. So when we fill those into our average rate of change formula, f of 70 is 40, f of 40 is 17, and then we just go through the arithmetic. So we have 40 minus 17 over 70 minus 40, which ends up being 23 over 30, which is approximately, and this is just estimates because we're doing, we're just reading from a graph. And so when we read from a graph, it's really just an estimation. And so what this value represents, this average rate of change, is that from 1840 to 1870, the population is growing. The population increases. At an average rate of 0.77, and the units here are millions of people per year. So during that time, the average rate of growth for the U.S. population was about 0.77 millions of people per year. All right. So if we wanted to know how fast the population was growing directly in the year 1840, and again, this is going to mean t equals 40 for the purposes of our graph. Another way to phrase that question is, well, what is the instantaneous rate of change for this function? At time t equals 40. And the instantaneous rate of change is just the derivative evaluated at 40. And what is the derivative in terms of a graph? Well, it's just the slope of the tangent line. So here, we don't actually have a formula for our function that we can do the derivative of. We just have a graph. And so how do we estimate the derivative in this case? Well, we look at our point on our graph, and then we draw in what we think the tangent line should look like. So this is, I have it already drawn here, but part of the process would be us just drawing in that tangent line for ourselves. So we have our function f of t, our curve, and then we have our tangent line at t equals 40. All right, so to estimate the derivative, really this comes down to then just estimating the slope of that tangent line. And the way we can do that is just by kind of what we did before. Pick a second point on that line. So try to make it as easy as possible. So I might look at, say, this point here, goes through a grid line. And that looks to me to be at 60. And then I would say maybe like 27 as the y value. And then what did we say for point P? That was at 40, and that was about 17. Again, just estimates here. So to do the slope is change in y over change in x. So 27 minus 17 over 60 minus 40, which ends up being 10 over 20, which is 0.5. And so directly at t equals 40, what this value is telling us then is that in the year 1840, the population was growing or increasing. We know it's increasing because that slope is positive. It was increasing at a rate of 500,000 people per year. So even without an actual formula for our function, if we just have the graph, we can estimate the derivative by drawing in the tangent line for ourselves and then estimating the slope of that tangent line. And so in the context of this problem, the derivative tells us how fast our population is increasing or maybe decreasing in terms of millions of people per year. All right, let's try the last part here, where we just compare the rate of change at two different times. So we want to compare, well, in the year 1810, is our population growing faster than in the year 1860? So when we see this word when we see this phrasing growing faster, really what we're thinking here is instantaneous rate of change. And for this problem, 1810 corresponds to t equals 10, and 1860 corresponds to t equals 60. And so we plot each of those points on our graph, and we look at the slope of the tangent line in each of those. So we have our original population curve there. And then the dotted line here, this is our tangent line, what we would actually draw in ourselves. I've just included it here. So the tangent line at t equals 60. And then the solid line, this is our tangent line at t equals 10. And we want to just compare which of those tangent lines has a larger slope. And we see that it's at t equals 60. So since the tangent line at t equals 60 is steeper, the slope is larger. So since the slope is larger at t equals 60, we can conclude then that the population was growing faster in the year 1860 versus the year 1810. So 1860, our population is growing faster than it's growing in the year 1810. And we can see that because in 1860, or at t equals 60, the slope of our tangent line, it's going up faster. So it's a steeper tangent line. All right, so just a little bit of practice kind of interpreting what the derivative is in terms of, well, graphically, and in terms of a population function. Next, we're going to see how to estimate a derivative numerically where we're only given a table of values. And so how we're going to do this is with a difference quotient. So in this example, the function d of t, which we've described in the table there to the right, gives the national debt of the U.S. at time t. And what we want to do is we want to calculate the derivative in the year 2010. So we want to calculate d prime at 2010 there. And we know that if we had a nice function, nice formula for our function, we could do this with a limit. Now, we don't have a nice formula, so the best we can do is just work with this difference quotient. So, as we've seen with limits, there's two ways t could approach 2010. We could approach on the right side. So we're going to look at a right side difference quotient. And then we could also approach from the left. So we'll also look at a left side difference quotient. So what do we have to work with in terms of, and what is our difference quotient? Well, it's this gadget here without the limit. So right side means we want to approach 2010 from t values that are larger. So we would consider, say, using 2010 and 2015 to calculate our difference quotient. So we're going to use 2015 and 2010. We just look those values up on our table. So when we look 2015 up on for our function value, it's 18,922.2. We look up 2010 on our table there, and the function value is 1,425.2. And then we get 5 in the denominator. And if we do the arithmetic here, we get 979.4. And we'll see what that value represents in just a second. But right now we're just trying to estimate the derivative using difference quotients. So that was the right side. Now we could look at a left side difference quotient. And so we want to approach 2010 with values that are smaller, time values that are smaller. So here we might use like 2005 and 2010 to do our difference quotient. So d of 2005 minus d of 2010 all over 2005 minus 2010. Look those values up on our chart. So 2005, when we plug it in, we get 8,170.4. And then the same value we saw, 14,025.2 for the year 2010. Do the subtraction in the denominator, we get -5. And then if we do our arithmetic here, we end up with, what do we end up with? 1,170.96. Now, clearly, you would need a calculator to do these calculations, but these are actual numbers. You can go onto the Treasury Department's website and look these values up for yourself. So these are actual year-end results from the Treasury Department. You could look them up yourself. All right, so to actually then use these values to estimate our derivative, what we'll do is we'll just average the results together. So the derivative at 2010 is going to be approximately equal to the average of these two results, of these two difference quotients. So we just average them. To do that, you just add them together, and since there's two of them, we divide by 2. And what do we get? We get 1,075.18. And so what this value represents is that our national debt, the national debt of the U.S., is increasing, or it was increasing, at a rate of approximately 1,075.18, and now the units here are billions of dollars per year. So that's what this derivative d prime at 2010 represents, is it's telling us that our national debt is increasing approximately at a rate of 1,075.18 billions of dollars per year in the year 2010. All right, so that's how, if we just had a table of results or a table of data there, how we would estimate the derivative using difference quotients. And so the one thing we were doing in each of these examples is we were looking at the units. We were keeping track of the units. So the unit of measure for f prime is equal to the unit of measure for function f divided by the unit of measure for function x. And we generally call this, we read this division, we read that division line as per. So in our population example, we had function f of t, which gave the population of the U.S. in millions of people t years after the beginning of 1800. Well, the units of measure for function f were millions of people. The units of measure for time t were in years. And so when we talk about the units of measure for f prime of t, we read that as millions of people per year. Same thing that we saw in our national debt example. We had the function d of t, which described the national debt of the United States at time t. And in that example, our function, the units for our function were billions of dollars. Time was still measured in years for that example. So when we looked at the derivative d prime of t, what were the units? Well, they were billions of dollars per year. So it told us how fast our debt was increasing each year. And we've also looked at, so today we've looked at this population and national debt examples, but in the past we've looked at objects moving in a straight line. So we've looked at instantaneous velocity. So we've considered the case where s of t is the height of an object that's moving in a straight line. So maybe we drop a ball or a rock from a tall height and we watch it fall down. And let's suppose that for some specific function s of t, it's measuring the height in meters and time is being measured in seconds. Well, for velocity then, the units of measure for our position function are meters for that example, or we'll just abbreviate that m. Time is seconds, which we'll just abbreviate s. And so when we think about velocity, which is really just our derivative s prime, what are the units? Well, just meters per second. Or just m, which we denote m over s like this. Now there is also another function that we can define called acceleration, and the acceleration is just the derivative of velocity. So we could look at the units for acceleration. What are the units for velocity? Well, they're meters per second. So m over s. What are the units of time? Well, they're seconds in this little example. And so the units for acceleration, which is just the derivative of the velocity function, would be meters per second per second. Or to denote that, we would be m over s squared. So just a little bit more context for the examples of doing velocity, and now we've seen how to do acceleration and what the units would be for each of those in terms of the derivative. All right, so we're going to stop there for today. And like I had mentioned earlier, your exam is going to be, your graded exam will be available on Gradescope. I'm going to release the results in a few minutes. So just keep an eye out for that. In recitation today, you should kind of review over what you got wrong on the exam and, go to recitation and, really try to understand where you went wrong. And then for next time, you'll be able to retry that question, well, something very similar, on the next exam, which is next week in recitation. So for today, recitation, you can, or for this week rather, for recitation, you can go over the exam questions from last week and then any homework questions that you might have as well. So start preparing for the exam for next week. All right, we'll stop there for today. Have a good rest of your Tuesday, and then we'll see everyone for lecture on Thursday. Bye-bye.